Welcome to this explainer. Right now, unseen physical forces are literally smashing into your head at over 700 miles per hour. Crazy, right? And yet your brain is just smoothly interpreting those collisions as the sound of my voice. Today, we're diving way past the basics. We're going to explore the deep physical mechanics of acoustics and sound propagation, and basically make the invisible world of acoustic energy completely visible. So, what exactly happens when an object vibrates to create sound? To kick off the life cycle of a sound wave, we gotta look at that very first moment of creation, the vibration itself. Picture striking a tuning fork or, plucking a guitar string. That object doesn't just buzz in a vacuum. It physically shoves the air molecules immediately around it. It's a purely mechanical action. The vibrating object smacks into an air molecule, which then smacks into its neighbor, setting off this incredibly fast chain reaction. That cascading domino effect of physical pushes, that is the literal birth of a sound wave. You see, sound is a transfer of actual physical energy, and fundamentally, it absolutely requires a medium to travel or propagate through. That medium could be a gas, like the air we're breathing right now, a liquid, like ocean water, or even a solid, like a steel beam. Without a medium, say in the dead vacuum of outer space, well, there are no molecules to push. So no matter how hard you smash that tuning fork in space, zero sound energy gets transferred. It remains totally, perfectly silent. All right, let's start at the beginning with section 1, the birth of sound. We often default to picturing waves as transverse, like ripples moving up and down on a pond. But sound behaves completely differently. It is a mechanical, longitudinal wave. This means the particles of the medium actually move parallel to the direction the wave itself is traveling. Instead of bobbing up and down, the molecules are constantly pushing forward and pulling back. This creates distinct areas of high pressure, called compressions, and areas of low pressure, called rarefactions. Think of it like a rapid pulse of pressure just zipping straight through space. Now that our wave is moving, let's move on to section 2, the anatomy of a wave. Let's break down its internal DNA. These four metrics act like a literal control panel for human hearing, basically bridging hard science with how we actually experience the world. First up, frequency. This measures how fast the sound wave vibrates, and it translates directly to the pitch you hear. High frequency, high pitch. Then there's amplitude, which is the physical size or power of the wave, and that determines loudness. A larger amplitude physically pushes on your eardrum with way more force, giving you a louder volume. Meanwhile, wavelength is the actual physical distance between two consecutive wave cycles, and the time period is exactly how long it takes for one full cycle to finish up. Together, these properties mathematically define literally every single sound you've ever heard. Now, as this perfectly structured wave travels out into the world, it doesn't just stick to one constant speed. It actually speeds up or slows down based entirely on its environment. The speed of sound depends heavily on the density and the temperature of the medium it's passing through. Since sound relies on molecules physically bumping into each other, it travels much faster through dense solids or liquids than it does through the air. This is exactly why low-frequency whale songs can travel for thousands of miles through the dense, conductive medium of the ocean, while a scream in the open air just dissipates into nothing in a matter of seconds. Oh, and even in the air, warmer temperatures give molecules more kinetic energy, which means the wave propagates faster than it would on a freezing cold day. All right, so our sound wave is traveling fast, zipping right through its medium. But let's pause and ask a super practical question. What happens when it encounters an obstacle it just can't easily pass through, like a massive brick wall or a sheer cliff face? That physical energy has to go somewhere, right? Which brings us perfectly to section 3, the science of echoes. When sound energy hits a dense barrier, it experiences reflection. It's a lot like a tennis ball violently bouncing off a concrete wall. But in enclosed spaces, this gets incredibly chaotic. If a sound bounces back and forth multiple times across different surfaces, think about clapping your hands inside an empty cathedral or a tiled bathroom. It creates what we call reverberation. The reflections all blend together, causing this prolongation of the sound that slowly decays over time. It is the exact same acoustic energy, just trapped, overlapping, and bouncing around until it eventually fades away completely. But here's the cool part. We don't just passively listen to echoes, we actively harness them. We use the power of acoustic reflection in everyday tools. Take a megaphone, for instance. Its cone shape purposefully reflects sound waves bouncing out from the speaker's mouth, focusing them in one single direction, rather than letting all that energy just scatter uselessly. A doctor's stethoscope relies on the exact same principle. It picks up the faint, low-frequency thump of a heartbeat and reflects it continuously up the internal walls of those rubber tubes. that guides the acoustic energy directly into the doctor's ears with just incredible efficiency.
Finally, let's dive into Section 4, Beyond Human Hearing.
20,000 hertz. That massive number represents the absolute maximum upper limit of a healthy human's audible hearing range, which, by the way, starts all the way down at a super low 20 hertz. If a wave vibrates at, say, 25,000 or 50,000 times per second, the acoustic energy is absolutely still there in the air, but your eardrums simply cannot process it. It becomes completely silent to us. We are officially entering the realm of the unseen and unheard. But listen, just because we can't hear it definitely doesn't mean it isn't immensely powerful. Once a wave pushes past that 20,000 hertz threshold, it officially becomes ultrasound. And ultrasound possesses incredible hidden mechanics that we utilize across huge industries. Because of its extremely high frequency, it can be used for precision cleaning. The tiny, super rapid acoustic vibrations literally shake microscopic dirt and grime right off delicate jewelry or surgical tools. It's also used in advanced manufacturing to detect invisible structural flaws deep inside solid metals, because those high-frequency sound waves will reflect differently if they hit a hidden internal crack. And, of course, we use it for advanced medical imaging, safely bouncing those sound waves off internal organs to accurately map out the human body without making a single incision. The most impressive macroscopic application of ultrasound is undoubtedly sonar, which stands for Sound Navigation and Ranging. It's an absolutely ingenious, large-scale technology used extensively for underwater measurements, complex naval navigation, and finding submarines. Let's break down exactly how sonar maps the deep ocean. First, a ship on the surface emits a high-powered ultrasound ping directly downward. Next, that longitudinal wave travels steadily through the dense medium of water, all the way to the ocean floor. Then, the wave hits the solid bottom and reflects right back up to the ship. Finally, onboard computers track the exact time it took for that round trip. Since we know the precise speed of sound in water, we can use that time to calculate the exact depth. By continuously sweeping these pings, ships can essentially see with sound, rendering massive, real-time 3D maps of jagged underwater mountain ranges purely using invisible echoes. How amazing is that? As we wrap up this explainer, these core takeaways pretty much summarize the incredible life cycle of a sound wave. We've seen how sound isn't just noise, it's a transfer of vibrating physical energy, propagating as a longitudinal wave. We've learned that the mathematical properties of frequency and amplitude dictate the pitch and loudness of the world around us. We explored how these waves bounce off dense barriers to create echoes and complex reverberations. And finally, we revealed how high-frequency ultrasound pushes right past our biological limits, letting us do everything from looking inside the human body to mapping the bottom of the deepest oceans. The world is vibrating with information. You just needed to know how to see it. But as we continue to push the boundaries of extreme frequencies, from acoustic levitation that can physically hover objects in midair to highly targeted sonic weaponry, we really have to ask, what invisible barriers will sound break through next? Thank you so much for watching this explainer, and keep exploring.